So we're in chapter 18, section 2, and we're going to be talking about hydrocarbons. This is in your chemistry book. So there are many organic compounds. So we're talking about organic compounds, those with carbon, but there's very many that contain only hydrogen and only carbon. And they call these hydrocarbons, of course. And many of these are derived from petroleum, coal, natural gas, and they're a vital part of our industrial economy, of course. And in fact, about 90% of hydrocarbons are used as fuels. And they also serve as raw materials in a lot of different other organic substances. And so that's what we've been talking about is organic substances, right? And that's those with carbon. And other substances that are hydrocarbons are like plastics, lubricants, synthetic rubber, medications, and they come in a variety. Hydrocarbons come in a variety of shapes and sizes, ranging from very, very lightweight molecules of methane natural gas to very large molecules of tar and asphalt. So how do we classify these? Well, they're classified in a lot of different ways, but one of the simplest ways of classifying is basically classifying by their structures, right? Their molecular structures. Some of their molecular structures consist of open chains of carbon atoms, and other are classified as acyclic, which are basically cyclic or acyclic. If you have open chains like this here, this open chain, of course that's not in a cycle, so it's called acyclic. If you have a branch chain coming off, this too is acyclic. So as you can see here, you'd have hydrocarbons being branched, as this one is branching off. So here you have just basically all carbons and all the hydrogens around it. Each one, it's going to be a long chain probably. And here you have the branch chain that branches coming off from each one of these can go off in any directions now with hydrocarbons. So you can see how vast, different the different chains can be, depending. You have a variety of ways to go. And then we have the cyclic hydrocarbon here, and we have the carbons in a cycle here, and then you have the hydrogens all around the outside. And these are called cyclic hydrocarbons. So, and there's another way to classify them based on the type of chemical bonds they have. The chemical bonds, there's 3 different chemical bonds. One is alkanes, and alkanes mean they're only bonded by one bond, and then alkenes have double bonds, and then alkynes have triple bonds. And we're going to get more into this subject, and we'll show as we go into each one of these types. So going on to the cycloalkanes and cycloalkenes, some of them are, of course, cycles. Hydrocarbons containing one or more triple bonds are called alkynes, right? And very few cycloalkynes exist. Kind of hard to get triple bonds into a circle, I guess, but some do. So alkanes, alkenes, alkynes, and similar cyclic hydrocarbons are collectively called aliphatic hydrocarbons. Remember that word, aliphatic hydrocarbons. So, and the additional class is called aromatic hydrocarbons. So these are all called aliphaic. All the alkynes, alkenes, and such, alkanes, the 3 type, these are all aliphaic. And then, but the aromatic hydrocarbons differ. How do they differ? So they have cycles, they form cyclic, they form in a cycle, but they have what's called, they have delocalized electrons. So what is that, delocalized electrons? That means they have all of their groups, the electrons are shared by the whole group together. So, and we'll find out more about that later on. And you'll see the picture of it. It'll be like a circle inside. You'll have a cyclic, maybe a hexagram type cyclic. Then in the middle, you're going to have in the middle of that picture, that cyclic picture, you're going to have a circle. And that means that they're all, delocalized, shared with each other. And we'll see that later on. But those are the aromatic, which are different than the aliphatic. Aliphatic hydrocarbons basically are those hydrocarbons that we will be describing here. So they're not delocalized, So anyway, also hydrocarbons may be classified as either saturated or unsaturated. When you think of that, what does saturated and unsaturated mean? Well, saturated means you're full. You can't get any more, right? No one else allowed because we're saturated, and unsaturated means, yeah, we can take more. So alkanes are considered saturated since each carbon-carbon bond is just a single bond. So they can't take any additional atoms. But the alkenes and alkynes have double and triple bonds, and so they are considered unsaturated, and so they can take multiple bonds. So, and because their bonds can easily break because they have these multiple bonds into smaller, so they are considered unsaturated. They can accommodate additional atoms without breaking the carbon chain in itself. So because they have the double bond, so that's unsaturated, meaning that they have room for more, right? And then saturated. So that's important when we're dealing with hydrocarbons. So hydrocarbons come in just so many variety of forms. We'll find a lot of different, and like we said before, just remember a lot of them come from petroleum products. So, which is oil, right? So now we're going to talk about each one of them. We're going to talk about, first of all, about alkanes. And alkanes, and we're going to go over the formulas of those. Well, alkanes are aliphatic hydrocarbons, like we said before, containing only single bonds between carbon atoms. They're called alkanes. The first four members of the alkane series are methane, ethane, propane, butane. So let's look at those up here. Here's the structures. So these are alkanes. They only have, as you can see here, they only have one single bonds between the hydrogens and the carbons. So here we have a CH4 is the simplest kind, and the structural formula here. And this is methane, and you can see how this is the ball and stick formula and the space formula, same way, but you can see this is the basic one we can see. Ethane, of course, we're going to have CH3, CH3. So here we have CH3, CH3. See how we're going through here, like 3 and 3 together. Here's the ball and stick, and there's a space. This is ethane. Propane, we're going to have CH3, CH2, CH3. So in the midst, we're going to here's what we have. We're basically having the carbon chain getting bigger. See how the carbon chain is getting bigger? With the hydrogens all coming around. And here we go with propane, and here's a picture of the ball and stick in the space. Here's butane, and this we have 1, 2, 3, 4 carbons with all the hydrogen around. Butane. So these are the first 4 alkanes, although they go on and on. So here we have the prefixes used. Meth means 1, eth means 2, prop means 3, but means 4, pent means 5, hex 6, hept 7, oct 8, non 9, dec. So these are all, and they'll use these on ane. It's always going to be ane because they're alkanes. And so you're going to find them going on in the midst. How fun is this, So that's how the alkanes are put together there. And as we can say, they're basically, unbranched. You don't see any branches coming out with 5 atoms. And so we go on, if we had pentane and octane, we go on in that series. And then the basic structural unit will be, with the ends are going to be capped with hydrogen. So we have those hydrogens on the end. Now, we could do a formula for this. So then we can go ahead. If we had a formula, the formula is C to the n power equal H 2n plus 2. So if we have, say we have 5 carbons, then we're going to have 2n plus 2. We're going to have 2 times 5 is 10, and we're going to have 12 hydrogen. So this is a good formula just with this. So N and H, 2n plus 2 is the formula. You can plug it in. If we had, say that we had 10, basically had 10 carbons. So 10 carbons, we would have 20 plus 2 would be 22, because there's 2 on the end. We'd have 22 hydrogens. And these go on and on. So the alkane series is sometimes known as the paraffin series. Paraffin, param means little, and affinities mean affinity. So, or attraction, because they do not readily react with other substances. They, with the exception of sometimes oxygen, it says there, but they usually don't react with other substances. And that higher molecular mass, when they get into a higher molecular mass, when we get up into the, we get up to the octanes and all these things and get up to the masses, we end up with something. Paraffin, when you think of paraffin, what do you think of? Paraffin wax. They become waxy, right? When they get as large numbers, they become waxy. And some of the larger ones are like solids like paraffin wax and petroleum jelly and those kind of things. So that's alkane. Now we have alkyl groups, alkyl groups, I should say, ALKYL groups. And these alkyl groups are basically fragmented off from our alkanes. So, and these are changed because of that. So with a name, so they're branched. So remember, these basic alkanes are not branching. They're basically all just hydrogen. Now we're going to have them branch off. And so we're going to have a group that branches off, and this is called a alkyl group. And so here's the picture of it. So here we have, here's the branch, going to be the branch. This is the red part's the branch. This is methane, and basically it has lost a hydrogen, so it's looking for a hydrogen. So it wants to get a hydrogen off from butane. Here's butane. Butane is just going and going, and it actually needs a hydrogen here. So it's going through, and the branch comes in. Basically, the branch of methyl group comes in and grabs that branch right there, and now we have this here. It's called methylbutane because methyl branched off the butane. So those are the alkyl groups, because here we know they're branches. Alkyl means they're branched off, and the alkyl is this little group that branches back on it to it. So just think alkane and alkyl, right? You're like, okay, gets kind of confusing there a little bit, huh? So on a little more about the alkyl group. So it's derived from, as these simple alkanes, the picture, and you drop the A-N-E and you add Y-L. So to the group, to know that it's an alkyl group. An alkyl group must be attached to the carbon chain and cannot stand alone. So if you have this, it has to be attached. Since all the carbon atoms must be from 4 covalent bonds, it has to be attached. So that picture, we already showed the picture, but I'm not going to show it again. A branched alkane is considered to be made up of a parent hydrocarbon. So of course the branch one is not the parent one. The parent one is the one it's hooked onto. And so the longest continuous chain of carbon atoms would be the alkyl groups. The branches and the names of the branches are going to be attached. So just knowing you have a parent hydrocarbon and then the other, and each carbon atom in the parent chain is giving a number which addresses. So the parent hydrocarbon is numbered in such a way that the smallest possible numbers are used for the addresses. So they got to give you addresses. So let me just show this. So here you're going to have the first group here. You're going to have, this is an alkane, the first group, the second group, the third group, the fourth group, the fifth group, as you're going on. So you can see this is the parent pentane. Here's 1, 2, 3, 4, 5 is 5. So it's a pentane parent. And here's the methyl group, attaching on. And so now they're going to say, where does it attach? It's going to be attaching in this direction, attaching on number 2. So it's going to be called the number 2 methyl pentane. So So it's not 4 pentane, as would be the case if the parent were numbered in the other direction. So they're basically numbering it this direction, so the molecule. So this is a hexane 1, 2, 3, 4, 5, 6, and this is 2, 5. So when you have 2 of them, you're going this direction. So you have one methyl that's coming off, methyl group that's coming off here, and it's at number 2. And then you have number 5, you have a methyl group. So you have 2 methyl groups, and this is called 2,5, because it's number 2 and number 5, dimethylhexane. So, and these are branched, and they still fit in the general formula. Cn equals H2n plus 2. It's always 2n plus 2 because you get 2 hydrogens on each side, but 2 at the end. Hydrogens have to be at the end too. So let's look here. The reactions of alkanes. So they are very unreactive, really. Very few reactions, and they need to have a high temperature to react. And when they do, they can maybe react with oxygen in combustion, and they can be used as fuels. So, of course, most of the hydrocarbons are from petroleum oil fuels. Anyway, that's when you think of hydrocarbons. I always think of petroleum fuels and oil. When you think of oil. So so at elevated temperatures, they do react with oxygen, of course, and that's why we call them hydrocarbons are combustible. This type of reaction is combustion. So here's a picture This is the combustion of alkanes. Here we have, as we go through, we have the hydrocarbon reacting with oxygen, and then they give off carbon. When you have a combustion, you're always going to give off carbon dioxide and water, and it blows up. But carbon dioxide and water come, and this is called combustion. And there's other fuels that are composed largely of alkanes, and there are natural gas, propane, butane, LP gas, which is propane-butane mix, gasoline, diesel fuel, jet fuel, and all of these burn similar and produce what when they burn? They produce carbon dioxide and water when they burn CO2 and H2O. If insufficient oxygen is present, poisonous carbon monoxide can be reduced. So if you don't have enough oxygen and they start burning, then they use little oxygen. So instead of CO2, they're going to produce CO, which is carbon monoxide, which is poisonous. So carbon monoxide could basically kill you, breathing in too much of it. That's why you need, whenever there's engines burning, say you have a car in the garage and you shut the car up, and you can get carbon monoxide poisoning because you don't have enough oxygen. So it's going to produce carbon monoxide poisoning. That's why you have those carbon monoxide detectors in your house. So here are the names of properties of selected alkanes. So methane, ethane, propane, butane, pentane, hexane, heptane, all the way through here, and you can see. And here if it's a gas, as you get bigger, as you get more carbons and hydrogen, it becomes liquid, all the way to isocyane, which becomes a solid. And so the name and formula of an alkyl group. So these are when a branch happens. It's going to be called a methyl, ethyl, propyl. All these things. These will be the branches. So the alkyl group is the branch that branches off. Just remember that. So they always have to have alkane. So alkyl needs alkane to be married to. So Kyle needs to be married to Cain. The Cain in that way. So let's say Lorraine, so but anyway, so Kyle needs to marry Lorraine, so the Cain. So here we go. Anyway, some way you can remember, just think Kyle and Cain, and the Kyle at the end, all these YL will be the branch, and Ain would be the parent hydrocarbon. So that's enough for alkanes. Let's go to alkenes. So now we're getting a little more complicated. We have, alkanes, alkyls, and now which are together. Now we have alkenes. Well, alkenes are aliphatic too, which aliphatic means that they're not delocalized. They don't have delocalized electrons. Is all it means. Is a delocalized electron is like a big cloud that everybody shares, So they're not communal, like communism or communal. They're all sharing, So aliphatic is what the basic is, what we're showing here. So these aliphatic hydrocarbons contain one or more double bonds between carbon atoms, and they're called alkenes. Alkenes is also known as olefin. The olefin series, and the simplest metal we're going to go all the way through is ethene. So we're going to have these same, like ethene. We're going to have these with only not ane. It's not going to be ane because that's an alkane. It's going to have ene at the end. So we're going to take off the suffixes and put on a ene. And all this means is that they're double bonds. And with double bonds, they're less to be, as for, when you talk about saturated or unsaturated, there'll be unsaturated because they'll take more. So anyway, here's all these double bonds. This is beta-carotene, which is vitamin A, I think. It's beta-carotene, and so important. So here you have the double bonds. See all these double bonds coming? Here you have, this is a large molecule on each end, but you have all these double bonds in the midst. So that means that this is an alkene because it has all, not all, but practically every place that doesn't have one, they have a branch, so because they branch out. Otherwise, they have double bonds throughout, and these double bonds make it an alkene. So it says alkenes are similar to those of alkanes, but the number of carbon atoms is indicated with the prefix. So you have the same prefix like eth, propyl, butane, and the suffix has to be ene, which I already went over. The general formula is going to be different than the other formula. Instead, it's just going to be for each carbon, there's going to be 2 hydrogens because they're sharing. So the formula is not going to be 2n plus 2. It's going to be just 2n because at the end they're going to be sharing. So the formula for an alkene is carbon, and for each carbon you're going to have 2 hydrogen is what that means. So, and it says when naming alkenes, you need to have an address given to where the double bond is. So each characteristic is different because they have a different bond in a different place. So if you have, remember how we did with the address here? So here you have HTC and you have a double bond there. So we know in the very first carbon, there's going to be a double bond. So they say 1 butene because there's butene basically how many carbons? 1, 2, 3, 4. So there's 4 carbons, but the double bond is going to be in the first one. And here's 1, 2, 3, 4 butene. Butene means it's an alkene. And where is that double one? It's going to be on the second carbon between the second and third carbon. So you say 2 butene. So on the second one, there's going to be, it gets pretty complicated, I know, but this is what this means when you have a 2 before. It's where that double bond is. You have to tell where that, just like we had to tell where the branch was, now we have to tell where that double bond is. So, and to find this, it's more to be specific. You can't just say butene because there's different butenes. It depends on where that double bond is. So there's so many different kinds, like thousands and stuff, kinds of different bonds. So we have to find out exactly where that bond is. So what are alkenes? What are they used for? So they're used for things like plastics, let's see, plastics, ethene, which forms polyethyl, and propene, which forms polypropylene, which are these, we're talking about, there's over 10 million tons of ethene are produced each year to produce things like antifreeze, solvents, synthetic fibers, as well as plastics. So a lot of times when you think of alkenes, you think of plastics. So, And just like alkenes, alkenes, just like alkanes, can burn in oxygen. That's why you think of petroleum. Of course, they burn very easily. Almost all carbons do. So here we have propene burning with the equation. This is equation how it burns, and it gives off what? Carbon dioxide and water. Changes their whole structure and just burns up and gives carbon dioxide and water. Carbon dioxide and water are always the result of combustion burning, right? And of course, alkenes are unsaturated. We already talked about that. So we'll know that. And they can form different compounds, so they have additional reactions. So for the example here, they have the presence of a catalyst such as nickel or platinum. And you can see here's the catalyst. Here they have the ethane. Basically, in the midst of that, anion can form. And they call this process known as hydrogenation. So hydrogenation is turning it back from, turning it into, I should say, from the ethene to the ethane. See how it happened? They got rid of that double bond. And in doing this, it's called hydrogenation. So, you think of hydrogenation, I think of, the hydrogenation of certain nutrients and stuff, where you don't want something to be go through hydrogenation, really adding that to it, changing it, the organic of it. But anyway, you have basically this hydrogenation basically is that of taking off that double bond and turning an alkene back into an alkane, somehow. So one of the bonds in the double bond between the carbon atoms break, and then they allow the hydrogen atom to bond to the carbons. So similar halogen molecules, you can actually now add halogen molecules such as bromine and hydrochloric acid. You can add acids, hydrochloric acids. So, and these are some of the pictures of halogenation is adding a halogen. Halogen, of course, are those, when you think of halogens, you think of chlorine and fluorine and iodine, and those are halogens. They're in that 17th column of the periodic table. And halogens, there is just basically halogenation is adding. They want to add bromine, it's a halogen to it. So here the hydrogens are replaced for bromine, so you call it halogenation. And here is hydrohalogenation. Basically, you're adding now, you're going to add hydrochloric acid. Chlorine is a halogen, So hydrochloric acid, HCl, is added right here, HCl. So you have hydrohalogenation, and that is adding hydrochloric acid to it. So these are alkenes. So let's talk about alkynes quickly. Let's see. Yeah, we'll get through this. This is alkynes. I know this is getting kind of long, but I think it's kind of important that we get through this. But alkynes are triple bonds. So, and of course, their general formula is going to be carbon, and it's going to be carbon and hydrogen 2n minus 2. Remember, alkanes was 2n plus 2, and alkenes was just n and 2n. Basically 2 hydrogens for each carbon. And now we have 2n minus 2 for alkenes. Now we're going to take off whether it's ane or take off that last one. We're going to add the alkynes. We're going to add YNE now to this. And so these are going to be alkynes. And so these are going to have a triple bonds. So these triple bonds, let's see, it's a picture of the triple bonds. See how the triple bond here, the hydrogen and chlorine, here's a triple bond here with our hydrogen and carbon, and you have the triple bond here. And so here's the catalyst, and then the pressure is getting rid of those triple bonds there, but here we go, have the triple bonds. So let's see, the ethine, when you think of alkynes now we're talking about, are the simplest, and they're called Ethine is actually called acetylene. Acetylene is in torches and hot flames, and there's also neoprene vinyl plastics are ethines with those triple bonds. And they're not really found in nature very often due to the triple bond is kind of hard. Usually they manufacture them in the laboratory here. And of course, those two bonds may break to form additional bonds. And here we have where the bonds could break and form additional bonds in the midst of alkynes. So let's see, let's go on here. We're going to talk really quick about aromatic hydrocarbons. So in the 19th century, scientists discovered hydrocarbons, unlike alkanes, alkenes, or alkyne, they had a different kind, and they called it aromatic hydrocarbons because, again, they had different characteristics. They thought, these are a different group. We had alkanes, we had alkenes, we had alkynes, you know, and now this is different. So these, many of these they call aromatic because they have pleasant aromas. And these compounds have cycles. They look like cycles. They're cyclic. But they differ in their properties from cyclic alkanes and cyclic alkenes. So in knowing this, we had a new category. Benzene is C6H6, and it's composed of a hexagon ring of 6 carbon atoms. Remember, I told you we'd get into these, with each carbon atom bonded to a single hydrogen atom. So now we have these carbon bonds that are bonded together, and they have a total of 3 bonds, but they have 6 valence electrons. So in the midst of this, they are not local. They're called delocalized. Remember I told you about delocalized? Here we go with the delocalized one. So basically they're sharing. When they say delocalized, they have like a electron pool they're sharing. And here's how they represent it. So here you have benzene. So you have benzene here, all the carbons, there's 6, 1, 2, 3, 4, 5, 6, benzene, and then you have the hydrogens on the outside. And then in the inside, you have them all sharing. It's in the midst of sharing here, it looks like a circle. So a lot of times they'll simply write it like this, meaning they're delocalized in sharing. So whenever you see this, and they might also write it like that, but that one is very common too. So in sharing delocalized benzene. So, and so just, you'll know, this whole thing actually can be attached to a branch too. So it gets pretty complicated. In fact, here's some polycyclic aromatic hydrocarbons, and see how basically the benzene is attached to each other, the benzene, you know, so we have methylalanine now because anyway, so benzene is toxic and it may cause anemia or leukemia. So if it's inhaled or ingested, you don't want to inhale or ingest benzene. Toluene is less toxic than benzene, and it's used as a solvent in certain adhesives. And then we have toluene. We also have styrene is a component in the manufacture of plastics. And then we have polystyrene, which is rubber, synthetic rubber. And the xylenes are used in the manufacture of other plastics and even gasoline. So here we have toluene, styrene, xylene. These are all aromatic, right? They all come in the category of benzene here. You see how benzene is? We have methylbenzene, phenylbenzene, or ethylene. Here's styrene, that's what we're talking about. And then we have xylene here. It's a picture of it. See how the carbons are located at one carbon, the carbon and hydrogens up here. This is a double bind, this one here. So here we have xylene, and here's benzene onto trinyltrilute. These are all these delocalized aromatic, you know. So, you know, aromatic, we talked about the aromatic being, they usually have, because of their smells, they're good smells, you know. Aromatic hydrocarbons are found in or manufactured from petroleum or coal tar. Again, they come from petroleum. Aromatic hydrocarbons are also used in the synthesis of dyes, insecticides, and medicines, aspirin and sulfa drugs are come from aromatics. And as a substitute group, there's also the phenyl group. So another type of aromatic hydrocarbon is polycyclic aromatic hydrocarbon, PAH. And this is containing into 2 or more aromatic rings that are fused together. And you'll have that. So PAH, coal tar contains a number of these. So we have naphthalene. Naphthalene is used to manufacture plastics, dyes, insecticides, medicines, and mothballs. Anthracene is found in synthetic dyes. Some PAHs that are carcinogenic as are found in soot and cigarette smoke, like nicotine, so some of them are cancer risky. Here's some pictures again. This is naphthalene, and this is anthracene, and anyway, this is the carcinogenic benzothracene. Benzopyrene here is carcinogenic, but here we have the pictures, and these are all delocalized, as they're sharing. We're sharing, all of these carbons are sharing in the midst of a pool of electrons in the middle. So these are we found those, these are pretty new. So let's stop there, we're getting long.